Okay, welcome everybody. Good morning. This is the third lecture. Let me first do a quick announcement or correction. Actually, the guy that invented the groups of intermediate growth was Grigorchuk. I'm not so sure if I used the right name. Okay, so this is you will see it in any reference properly cited. Okay, so another announcement. I am not sure that I have time to do so many exercises as I would like, and my decision was to write, for instance, this exercise 1.5, which we are going to use now, to send it to you by mail. Yeah? I'm myself not very satisfied with the solution of part D of 1.5. So you can read it critically and just, we can chat maybe tomorrow in the break if you have some kind of suggestion. I put this exercise, just taking it from Clara Leu's book without thinking too much. And I did not look very precisely, but it is an exercise with 2 stars, meaning it's a difficult one. So I tried to do it quickly, but maybe it's not completely correct, but at least it is an ansatz, and you can read it critically and then we can discuss it tomorrow. But I'm going to use it in a minute. So let me recap. I will have today less time for exercises because I really want to come to algebras. Yeah, this will give you more or less a complete picture of what I wanted to tell. Here again, the notion of amenability for groups, amenability for metric space, and I will give you, even if I have not much time, a little hint to solve this exercise 2.3, which refers to amenability. Okay, a group is amenable if here is our epsilon, our tolerance error. If for every epsilon positive and for any finite set of motions, dynamics in the group, I can find a Fellner set. Yeah, Fellner set is non-empty and finite. Yeah, somewhere. I'm not telling you where it has to be localized, but at least I have one finite, not empty set where the symmetric difference of the set and the moved set is compared to the inside very small. Okay, so on Tuesday, in the lunch break, somebody told me that the notion of symmetric difference of the symbol was not clear. Okay, that's very important. So let me just say it again for all of us. Say, if you have 2 sets, the symmetric difference of these 2, because they will appear in property A, they will appear all the time. Please ask me if you have some doubts. This is an important notion. Is everything which is in A but not in B union everything what is in B but not in A? Yeah? And this is, I don't know which symbol you use, but this is very useful in measure theory. If you have the union of A and B, then you want to chop it in 2 pieces which are disjoint. Otherwise, you have an inequality when you apply additivity of the measures. Okay, so that's an important notion which appears also here. Yeah? Everything which is in the moved Fellner set, but not in F, and everything that is in F, but not in the translated F. Okay, and this is a kind of boundary. Then we have the definition of amenability for metric spaces. Yeah? And one of the exercises tells you, please show to me that if the group is amenable as a group with this definition, first one, then it is amenable as a metric space because a group is a Cayley graph, and you can interpret it as a metric space, yeah, taking the path length within the graph. The definition is very similar. You have an epsilon, or for any epsilon, there is an R, which is the outer boundary. Sorry, for any epsilon and for any outer boundary, you have somewhere in the metric space a Fellner set, meaning that this is isoparametric relation is small. And the, sorry, the exercise is telling you, please tell me that these two things are the same. I'm insisting on that because I'm going to move from one definition to the other, depending on what is more convenient for me. Yeah, and the idea of the solution of this exercise, yeah, the difference lies here. You have a finite number of translations, yeah, because it appears here again. Oh, it does not, but it will in a minute. Okay, and here we have an R. Okay, in the relation, the trick, the thing you have to think is, or really the key point is that you define a number R. So imagine you want to relate this definition with that one. Yeah? You have a finite number of motions of dynamics, and then you take the collection of the length Remember, our groups are finitely generated. You have a finite collection of elements in the group, and each of it is expressed as a product of letters from the generating set. And now you take the max. Yeah? If you want to produce an outer boundary in the graph, in the Cayley graph, you have to push, you have to go along the paths that are defined on the graph. And this is done by moving the elements with generators. So if you have here the Cayley graph, I don't know, something like that. And you have this here, and this should be the corner set, and you want to go outside it, you have to move by generating sets. Yeah, so to arrive here, maybe you have to go along an edge which is labeled by S1, and so on and so forth. So this is the relation between the finite dynamics and the finite radius. Okay, I just tried. It's a good exercise because you get accustomed to these notions which are not completely. If you see them for the first time, you need some time. Okay, so we were standing here showing essentially that amenability is invariant under quasi-isometries. Okay, right. So you have a quasi-isometry. Let's keep the constants the same, CC quasi-isometry. And then since H is amenable, you have a Fowler set for, I'm taking the metric space language for an epsilon prime and R prime. I'm telling you in a minute what that is. Okay, and I have to show that G is also amenable. And I'm going to find a Fowler set, yeah, in G. Yeah? So in this case, X is G and Y is H. This is my Fowler set in Y. I'm fattening it and bring it back by the pre-image to a set F hat in G. Okay, so this would be F hat. Okay, and now I claim that this F hat is really a Fowler set in G. That's what I claim. And for that, let me just use the metric space language. So I'm going to produce an outer boundary of F hat. And then by 1,5a, this I mentioned, that's a very easy exercise. I can pull it forward with F and then back with the pre-image. Yeah? And then I get something which is essentially bigger, at least it contains this prime here. So you have a subset, you push it forward and then put it back by the pre-image. And you get something which is bigger in general. Okay? And then 1,5D, and Daniel just forwarded for you the solutions or kind of sketch and some ideas to the solutions. By the way, I didn't get the C squared. you can, I think you said it to me. There was one of the exercises here with a C square. It is the same because I can take always bigger and bigger constant, but I get a C. Just check my reason. Okay. So by 1,5D, the image of a boundary in X, yeah, of this F hat, is contained in the following guy. So I'm just expanding this here. Yeah, applying 1,5D for that. It is the boundary of the original Fellner set in H, and then the radius becomes scaled. Yeah? And the exercise you have to prove, and there is a sketch of solution. It's always the same. You go back and forth, and you pay the price of a rescaling of the radius. Yeah? And then you use again 1,5D. That tells you if you have a set whatever, it's a strange boundary here, but never mind, it's a subset of the target space. If you take it back with a pre-image, then you can bound it by a certain constant m times what you get here. So this is a strange boundary here. At least we have an upper bound of the original set here, of the original boundary. I have an upper bound in Y. And what? This is going to be my rescaled R prime. Yeah, you can already see. And then, but of course, an isoparametric relation has a numerator and a denominator, and I have to estimate from below the denominator to get a right estimate on both, on the quotient. This is, okay, this is just F minus 1 of the patent, Fellner set in G in H, sorry. This is by 1,115D, bigger than 1 over m times whatever guy you have in the argument. Okay? And then we are through. Because the isoparametric relation is this divided by that. And I have the right directions of the estimates. So I will get, essentially, it's smaller or equal than that divided by that. And then choose the radius r prime. I have, remember again, amenability is for any radius r prime in this case. Yeah, so I will adjust it to take r prime, which is this one here, CRC, and epsilon prime to get in the end an estimate below epsilon. I just have to take m squared, what do I have to take? Epsilon over m squared. In my original choice of Fellner set, which I have the freedom to do. Okay, that's the proof. Just take a look at the exercise and let me know if you also agree. Okay, so let's move to property A. This is not in Clara Loe's book. Many things of what I say are in Novak Yu's book. So if you want to read, if you like the topic, you can read more things there. Okay. Here we go. Maybe I can put it here. Okay, property A is a property of metric spaces, which in the case of groups contains the notion of amenability. So any group which is amenable has this property. I'm going to introduce it in a similar way. So maybe I can try to squeeze it here. So definition, XD has A, meaning has property A, and this was, maybe I should say, this was introduced by William Yu, 2000, working on Baum-Con's conjecture, which is a really difficult thing. But he invented this notion in this frame. Has A if for every epsilon bigger than 0, for any possible error, and any R bigger than 0, you see, very similar to this metric space amenability, there is an S, and there exists a bunch of subsets in X. This is also the new thing you have to deal with. Such that the following two conditions hold. The first one, I think, I don't need. The first one is a localization condition. Yeah. So these guys here are contained in a ball of radius S around X. Yeah. Any X. This I call uniform localization. These guys here, let me say, AX is not empty and finite. Remember again our leitmotif, and I hope I have time to tell you what nuclearity is next tomorrow. And this is again a finite approximation of the space in some sense. Yeah. Okay, so this is a uniform localization. So it cannot happen that the AX are can somehow expand depending on the point. Yeah, you cannot have them localized in balls of radius n plus 1. So there is a uniform bound to put inside the sets. And now comes the isoparametric relation, very similar to those that I have here, which tells you that the symmetric difference if X and Y are below R, so R is the radius that is given, then AX symmetric difference AY, in cardinality everything is discrete as in the whole course, compared to the intersection, this guy is smaller or equal than epsilon. Yeah. So I can put here a remark, or maybe the picture. The first remark is a picture. So you have here X, here you have Y. This is S, and the set AX is here, and the set AY can be a YP like here. And if the distance between X and Y is bigger than 2S, right? The two balls do not touch, then the sets are disjoint. Then AX and AY is the empty set. Yeah, this is what the localization is telling you. You localize them. If the points are far away, then the AX and AY will be disjoint. And the other condition here, the isoparametric condition, tells you that, can you see it from there? Well, if you are close to, if the 2 points are close, then essentially everything is in the intersection, so they don't differ too much. So this is the first, and then if the distance between the selected points is below R, then AX is essentially A. Yeah? Let me insist that this is a baby definition, yeah, of property A. It's not the one that gave Guoliani, but it is enough. Yeah? So let me say property A in inverted commas. Why? Because the sets AX and AY, this collection of sets has to have a multiplicity. But I'm avoiding this because this is too technical. And for the examples, I'm going to tell you that's enough. Yeah, so you have to imagine that for the real property A condition, you have the set in the space, and then a kind of label, a finite label that takes into account a certain multiplicity of the points in the space. That's unavoidable in the general theory. But let us do a summa chorus assumption. That's baby property A. Since this is recorded, who knows who's reading this? Okay, so a few examples. And maybe somebody is curious, I can tell you why you need the multiplicity. It has to do with the annoying fact that the pre-images of finite sets have cardinalities that change. Yeah, that's the point. You need to have a kind of place where to put these differences in cardinalities of pre-images. Okay. So examples. You know, when you teach the first, yeah, come. No, but you have to, yeah, that's why I put this word without the one. There is no prescription. In fact, the only thing it's important that it is uniformly localized. That's the point. Okay. The cheapest example, any finite set is has property. Yeah? The reason is just what? You can take as S localization the diameter if you want. And the symmetric difference of something with itself is the empty space. Yeah, this is for those of you that still are unsure with the symmetric difference. And so the quotient up there in the right blackboard from your side is 0. The second one, x is equal to z. I prepared the details, but maybe I can leave them to you. I tell you the solution, if R is positive. And now, since everything is discrete on Z, I would like to scale my precision with an actual number. So that's also very standard. Yeah, and then you grow with them, and somehow natural numbers are good are good as parameters. And so AK, so you take K in Z, and AK is just the ball. It's a ball centered, of course, at K. And you want to get a radius that somehow contains the original one and also the precision. Yeah? So you have a kind of inflated radius. Yeah, that's the key idea here, in which we are going to use it. And how much do you have to scale? Well, if I ask you this for a problem, then you just think, and sometime you get this radius. So in the radius, it's a kind of inflated ball. You have the radius you are given, yeah, and also the precision. And so if you want, this is K, and you go n plus 1 times r to the right, so somewhere here. One that way, and on the other side the same, minus k, no, sorry, k minus r, okay. And of course, here the s is already, you use both to write the sets. Yeah? So s is really, the localization radius is just this one here, because it's the same for all the AKs. Yeah, so s is, so property, the first one, the property A, no, not property A. I mean this one. Oh. Roman 1 and Roman 2 is 3. And now if you take an L in Z, such that the difference between R and K is below R. So you have an L that at most is at distance R. Well, then you see that essentially these two balls intersect in a big region. Yeah, because you cannot go too far away. Then you are scaling by m. You're very inflating the. If you put m equal 1, that would not work. But if you inflate the radius with m, you do the details. It's very easy. And then Roman 2 is simplified. Okay, great. Let me show for you. This I will go in more detail. Let me show for you that if G is amenable, then it has A. That's the next position. Sufficient. G is amenable. Then G has A. Let me avoid writing has property A. And if you look again, what is the main difference between group amenability and property A? The difference is, well, you have an isoparametric, you have here a symmetric difference. Well, here you have an intersection, but somehow the difference lies in the fact that the Faulkner set is somehow unrelated with the space. Somehow it's somewhere in the group, but it is not attached. So what would be the first idea one would get? Yeah? How can you prove this? You have to assign a set, but labeled by the point in the space. Okay. You have the dynamics, you have a product in a group, and it's obvious that you can relate it this way. So let F be a Faulkner set. Okay, let's do it correctly. Epsilon be 0 and R be 0. You have to give me a collection of spaces and a localization, uniform localization radius, and so on. So take since the group is amenable, then and you have a radius, I will choose R epsilon prime on to F. Let me delete now. Make this one. Okay. I can keep the radius, but I have to rescale the epsilon later when I'm through with the estimates as well. And of course, since this guy here is finite, this double inclusion, then it is clear that F is containing some bone of radius S centered at some point G if you want. Now, G naught, G. You take any one at random, and then you put a ball of radius S, and you get it in. Yeah, what are the AGs? Yeah, I have to give you a family of subsets which are labeled. Well, what do? I just take G times F. Okay, G times F. And if F, let me say H naught and H naught in F. And so these guys are contained because of the translation invariance of the metric. These guys are contained in the ball of radius S of G centered at GH. Yeah, so condition A, Roman 1 is satisfied. And now you have to verify the isoparametric condition. Yeah, and here you will see how convenient it is to have a dynamics and action product in the space. And so I have to compare the symmetric difference. So assume now that the distance between X and Y is below the radius. Yeah. And remember, we have an R Fernand's in G. Yeah, F has an R Fernand's. In particular, we have this relation here. And that relation here, I don't care. This one. I will need the usual amenability definition. Okay. And now I have to compare AG symmetric difference AH with AG intersected with H whenever I'm close enough. And close enough means the distance below R. And so I write down my definition, and that's GF intersect symmetric difference HF divided by the intersection of these two guys. And now I use the fact that the dynamics who asked me about semigroups. This step is not true for semigroups. I can multiply on the left by G to the -1, and I'm not changing the cardinality. The action, the dynamics in a group, within a group, is bijective. And this is what I'm going to do. And since I have not so much time, let me use Blackboard dynamics. Of course, the elements are going to be different, but their cardinality is the same. I can move on. And I'm doing this because I want to apply this symmetric difference. Okay. But I cannot really compare a symmetric difference with an intersection. I don't care. Now I'm writing, I'm multiplying and dividing by the cardinality F, and that's going to work. Okay, so I have done nothing, but that's further. This is small, this is further. Okay, so this guy here is below epsilon prime. I still don't know what is epsilon prime to get a nice epsilon at the end. I can tell you. And this guy here is close to 1. Okay? So this guy here is, if you want, below or equal than 1 minus epsilon. Okay. And let me leave this as a new exercise. I gave you some solutions, so it is fair to produce new exercises so that you don't get bored in the school. Yeah.
Is there the class of groups with the property A clause under semi-product?
Okay, so the class of amenable groups is very stable under semi-direct products, extensions, and direct limits, and so on and so forth. Property A is one of the exercises. It goes under subspaces. So if you have a space with property A, and you take a piece of it, and it has also property A. Not everything is stable under sub. Otherwise, I don't know what an extension is. Yeah, so you have to imagine property A in general is a property of a metric space. Yeah? And amenability, well, you have not much operations there. But subsets, it is stable under subsets. Yeah? In general, it's not so easy like in group. Yeah? But any, I would say no. Yeah, but maybe you wait until the end. I'm going to show you one of the big theorems in this lecture is to show that the free groups have and are not amenable. Yeah? So it's not so clear for a general metric space what are the stability conditions. The only thing I can say in it's an exercise is that it passes to subsets of the metric space. And for groups, I'm not so sure. Maybe I have to think. So,
about the sequence of one that goes to each, and then, I mean, if you have two groups,
yeah. Well, in the case of groups, you can do this. Not in the case of metric spaces. Yeah. I'm not sure. I'm not sure. I mean, if a group has A, subgroups have A too, but I'm not sure how stable it is in the other combinations. Maybe I can think about it. It's a good point. Okay, so what is the exercise? Don't try to make me forget it. Exercise to show that the other way around, maybe it's nicer. Show that F is below 1 minus F. Okay, it's very easy, especially for those of you that like to practice symmetric difference. We'll see. And then you can choose epsilon prime, gives you the solution. You can choose epsilon prime to be epsilon over what? 1 plus. Okay, so you give epsilon, and then in the end, I take a further set in the group, which is where epsilon is this guy here, and then you see that everything. Okay, let me now go to one minute. Yeah.
La desigualdad es al revés.
¿Perdón?
La desigualdad es al revés, ¿no?
Sí, pero es que le da la vuelta.
Ya, y cambia sentido, ¿no?
Bueno, claro, lo que está abajo está ahora arriba. No, ¿me explico? O sea,
la que coge golpe es la contraria de la posible.
De orden, digo de orden de la desigualdad. Es mayor.
Sí. Esta, ¿no? Esta. Okay. Okay. Now, proposition. And this is a really nice proof. Yeah, I like it very much. So that's why I don't want to proposition. Any infinite tree has property A. Yeah, that's really a nice thing. Any infinite tree actually any tree, because if it's finite, then we know it has A for sure. But non-trivially has A. Any infinite tree has A in particular, any free group, any F(n), or if you want, we have only Manax F2, so let me say in particular F2 has A and is not amenable. Remember the paradoxical decomposition we had last lecture, has A, but is not amenable. And now comes my doubt, because now I can mix amenable groups with non-amenable groups. Now I can do extensions, compositions, and I'm not sure. I know that the class of amenable groups is very stable, but I'm not sure if I can mix my two with an abelian group, and I'm not so sure. Yeah. Okay. So proof. So we are really defining something that already at the level of groups is way more general. And let me also mention here as a remark that if the group is amenable, then it has A. But not a metric in general, it is false that a metric space is amenable implies that it has A. Yeah, the counterexamples are difficult. So beware. If you want metric space amenable, then it does not follow F XE as A. It was a mistake I did in not in a written form, but I was asked, and I was mixing groups with metric space, so beware, it's not true. I cannot give you the counterexample because it uses box spaces, it's a complicated one. But anyway, and you can see it from the proof. You need to move. You need to have some kind of action. Yeah, that's what is missing in a general metric space. Okay, so the proof is so nice because it's a picture. And you also understand what the proof of better, what we mean by property A. Okay. So a tree, what is a tree? A tree is a graph which is connected and has no cycles. Yeah? So you can move from any point to any point in a tree, but you cannot find a cycle in there. Yeah, that's the definition of a tree. And if the tree is infinite, if this tree is infinite, then there is always a path of infinite length. It's quite reasonable, but it's based on a result by König, and it's called König's lemma. It tells you precisely that. If you have an infinite tree, meaning that you have infinitely many vertices, then there is at least one path which is infinite. And these paths are called ways. Yeah, by König. There exists a ray, which is an infinite path. Okay, let me do the picture here. So let me take a distinguished vertex. Let me denote well, maybe I don't have to be too formal. These are the vertices, the address, and I take a distinguished vertex, which people in graph theory call a root, some kind of choosing a zero. And now I have here my tree. And this is the direction that goes to infinity. And I can always choose a root at that starting, for instance, here. Let me just put it in yellow. So this is my root. I have an infinite path, and I take a point, a vertex in this path, and I can continue up to the point x. So imagine that that we have, we call this path omega. Omega is the infinite path starting at the root x. Okay. Yeah, there is an infinite path, and I can go to hit one of the points of this path because the graph is connected. And so let me imagine that we have an infinite ray that starts here. But that's a tree. You may have kind of bifurcations. So you may have many infinite directions. I know this way, this way, this way, this way. You can go here. Okay, so omega is the ray starting at the root. And what is the idea? Let me change colors. Right. Okay, 22 colors. So imagine that we have x here. We have to produce to show that it has property A. We have to produce subsets in the tree, yeah, which are somehow labeled by the points and the vertices in the tree. So let me take this x, and maybe this from here, y. Yeah. And let's choose also an R positive, and again an epsilon, which I would like to scale again by a natural number, as I did with Z. When I prove for you that Z has property A. In fact, it is an unequal group, so it has to have property A. But the construction of the A sets, yeah. Let me just scale now this way. Yeah, so for this R and for this epsilon, I have to give you the S and the bunch of subsets AX. Yeah, and so let me take this X. Since the graph is connected, I can go with X to the root, X naught, and then follow the infinite path. This I can do. Again, this is not true for a forest, but it's true for a tree. And then up to infinity. Okay? And you do the same for one. And this I can always do. I'm not, you can see it. I can take my train up to the root and then away to infinity. Yeah, and then continue. Okay. And so what are the AX and AY sets? Remember, AX has to be finite and non-empty. And what do? You just say, let me call this path the lila one omega y, and I cannot do any more lila. And the blue one I have space. So if you want, it's the extension of the original ray omega up to x or up to y. And then, I need them. And so what is you take this ray and you cut it with a bow, with a scaled bow. It's the same idea as in Z. But now you may have many pieces of set. Okay, and then you scale it, you intersect it with a ball centered at, of course, X with a uniform radius, okay, which is, of course, R n plus B. So in a sense, your AX set, you don't go up to infinity, but you stop at a certain point, say here. So you start at Y and then you move up until you have reservoir of distance. Yeah, and so this here would be AX, AY, sorry. And maybe this guy here, which is closer to the root, can go a bit deeper inside the set. So this would be up to here, this is AX. Okay, so the same with the Y. You take the extension of the infinite omega up to Y, and then you intersect with the ball between Y, and then Roman Y is trivial. You take just this expanded, so S is going to be R times n plus 1. It's exactly the same idea as in Z. Yeah? In fact, if you really understand the problem with showing that Z has property A, then you can easily understand why a tree has also A. Okay, and then it's not very difficult to show that so Roman 1 is check, and if you take 2 points X and Y that are below R, then it's not very difficult to see that this is smaller than 2 points. So why that? Because the distance between X and Y, the distance between these two guys is smaller than R. So the worst that can happen is that the distance from here to here is 2R. Otherwise, you have some kind of joint piece of the path inside the common infinite ray omega. Yeah. So the distance from here to here cannot be bigger than 2R in any case. Yeah. So you have a uniform boundary. What happens to the intersection? So imagine you can, X and Y can be within omega if you want. That's very convenient. Then you have a smaller symmetric difference. Yeah? But the worst that can happen is 2R. And what is the intersection? Here you use the fact that the AX and AY are defined through a scale. Yeah? So you want, this here is R times N times R. Yeah? And you know that the distance is smaller than R. So maybe you can consume this R here, but not that one. Okay, so the most part of the AX and AYs lie within the same piece of the path omega. Yeah? And then this is bigger or equal than N times R. You can lose at least one R set of points, yeah? But not the N times R. And N is growing, that's the point. Yeah? Now let me use again the backward dynamics. Okay, and that goes, this is smaller than epsilon. Here's my two. Okay, that's the idea. It's a really nice proof because there is not much to write. Okay, maybe this is the right point to make an end because I'm, okay, no. Let me just state the theorem without proof. And then we do a break. Yeah, the theorem without proof is the following. I think if you follow up to until now, you will believe it easily. Theorem. I will not prove it because I cannot do it with the baby version of A. I need the multiplicity. So my AX are in reality a subset of the space times a piece of N. So a kind of reservoir of multiplicity. This is for the correct proof, but I don't want to enter because this example, which was important to me, and the proof of the amenability of proofs implies property A. This does not need this multiplicity and one. But in any case, you will believe that if so if you have two metric spaces which are quasi-isometric, then the second one Y has A, then X has A too. In other words, property A is a quasi-isometric invariant metric space, the same as amenability. Okay, and the idea of the proof, if you have a quasi-isometry to X to Y, and Y has A, you have a bunch of subsets Bx of By. As ever, you want to pull them back by the quasi-isometry to X. Yeah? And then you want to, in inverted commas, define the A sets in X by 3 images. And if you spend some time with the exercises, you will see it's a headache. You know? The point is that the pre-image point in Y has a finite number of points, but this cardinality is changing. And that's why you need to extend A of X with a little piece of N, yeah, to keep track of the multiplicities. They are irrelevant because quasi-isometries are stable under perturbation of finite sets. But if you want to write, but the idea is at least it's this one. Take back the B sets to X this way. Okay, now it's 2 minutes to 12. Let's do a little break. Okay, what I'm doing now, and maybe tomorrow I'm going to relax. That's very difficult. So don't be frustrated if you don't follow all the details, but at least at some places, some ideas or some reasonings should be understandable. For me, it was very difficult to choose, to select in this universe topics. Yeah? So this is really advanced. Florian, you wrote this paper in Investigaciones 2000. So you can just kind of scratch the surface of the notion. Don't be frustrated if this is really true, but take it as a little show. Yeah? The importance of property A is its relation to Hilbert spaces. I want to end with operators. That's my aim. Yeah? And what is really incredible is the last theorem the last proposition I'm going to mention to you, which is if I have a metric space XT with property A, then at large distance, this guy is a piece of a Hilbert space, can be embedded coarsely into a Hilbert space. And this is really shocking, yeah? Because that's something that has no linear structure, that has no scalar product, and nothing is essentially at large distance a piece of a Hilbert space, which is Euclidean geometry. Is really, at least it was shocking to me for the first time I realized that. Okay, so let me do a first step towards this direction. Yeah, and then I will stop with chapter 2, and I will start with operators. I would like to motivate that even if if this seems to be a metric property, it's somehow at large distance characterizing Hilbert spaces. And I'm going to do operators on Hilbert spaces tomorrow. Okay, and so the Hickson law, in the same way that amenability is characterized in 10 to the 10 to the 10 to the 10 to the 10 different, completely disjoint ways, also property A has this property, this quality. Yeah, and so let me just do a first step towards Hilbert spaces. So XP has bounded geometry. Remember again, the balls in cardinality are bounded uniformly over the whole space. And I use it in the exercises. This uniform bounded geometry I use in one of the exercises I sent you. Okay. Then, this bounded geometry, this guy has A, even over in. There exists. For every epsilon, I promise you many epsilons in every R. There exists a map psi from the space to a Hilbert space. This is a complex separable Hilbert space with scalar products. I hope you are familiar. Maybe I should have said this. I hope you are familiar with the geometry of Hilbert spaces, you know what a scalar product is, what is an adjoint, etc. Otherwise, let me know. So what? There exists a psi, which maps the metric space into the Hilbert space, and there exists an S, yeah, somehow related to the S we have here. And such that Roman, I wanted to write A, but maybe it's not the right thing. Remember, psi of X is a vector, and the norm is 1. So you are on the unit sphere of the Hilbert space. Yeah, so this is the norm in the Hilbert space. I'm not writing it all the time. The second condition, it is kind of remnant of this localization condition. If let me put in color what we have given here. Sorry, the new things. So this guy has, and this guy is new. This is a completely new thing. Yeah, and it's that. In fact, in many books, many references, they define property A in this way. But I prefer to go from the set theoretic close to groups, yeah, towards here. The second condition B or Roman 2 is that if the distance between X and Y is bigger than S, then the vectors Cx and Cy are 0. So somehow the translation of being disjoint at the level of Hilbert spaces. Yeah. And the third one, here, Roman 3, what happens if the distance between X and Y is smaller than R? Yeah, so this kind of smaller than R, then the vectors in the Hilbert space are given. So this is a way of translating this isoparametric condition into Hilbert space. Okay. So this is our normalization. This is not very, and I'm not proving it. I'm not proving it because I want to spend time improving this coarse isometry into Hilbert spaces. Yeah, but let me at least give you an idea of the proof. At least that you see that it is not completely unthinkable to have this equivalence. And So somehow the Hilbert space could be, and in fact, tomorrow we are going to deal with that Hilbert space, giving a metric space this way, we found the geometry. It's not in the same way that if you have a group, you can consider the L2 space over the group, yeah, with an orthonormal basis of delta functions. So instead of using n, you're accustomed to little n2, yeah, where your labels are just points in the natural numbers, delta 1, delta 2, delta 3, etc. This is little n2. Well, why not taking, if everything is discrete, all the geometry, why not taking the group or a metric space as a Hilbert space? Yeah? So if you have a metric space, you found the geometry, you can consider this Hilbert space. Why not? Yeah, so these are little n2s, infinite sequences, squared summable, labeled by the points in the space.
These are real numbers, first of all, real numbers or complex numbers?
I am a mathematical physicist, I would say sido. Yeah. But I guess it's not so important here.
Yes, it is.
That's true. We can talk about that.
No, I mean, maybe it's the same for this. For me, it's important.
Okay, so let's say C width. Yeah, and delta x, y is just as usual, 1 or 0, depending if the label and the argument are the same or disjoint or different. You get one of them. So so you have 2 times the metric space. One as a parameter of your mappings, and then as an argument. So one way to use the sets AX and Y is to use one way to connect with the functions of the space is through characteristic functions. And then you normalize. These guys are empty, have a non-zero cardinality, I can normalize with them. And then, yeah, and this is kind of a characteristic function. Set lies in AX, and it's 1, otherwise it's 0. So that's the connection. Yeah? Maybe it is obvious that the norm of this guy is 1. Because essentially you are summing 1s over only when Z is in AX. You do it cardinality of AX times. It's 1. Cheap, huh? If the distance of X and Y is bigger than S or S, then the supports of these 2 guys are bigger than are disjoint. And so you get condition 2. And this one here is also not very difficult, but long. It's not the cheap condition to check in the Higgs and row characterization. These are new, not completely new, but relatively new things. Yeah, 2005, 2004, really advanced research results. Okay, let me not say more on that.
Una duda de notación. Cuando pone la chi super x, ¿qué se refiere? ¿A imagen de x sobre chi? O...
No, cuando... a ver, yo tengo, en lugar de tener una colección de conjuntos, instead of having a collection of sets, AX, I do have a collection of mappings. And each of it is a map from X space to H. Okay, so this guy has an argument which also eats points in the space, but it's labeled by an X. So the X plays the role of labeling the mappings in the same way that I label the set. But then I have to go to an L2 of X. So, yeah.
Pero este último mapa no iría de A super x a H, entonces. No va de todo el conjunto, sino va del...
No, lo que tiene es el soporte de los sujetos.
Ah, vale. Sí, el dominio de definición, el soporte es sobre A sub X.
No, está definido en todas partes. Pero el soporte es,
Vale.
solo es diferente de cero.
¿Has dicho que te dijéramos si nos estamos familiarizados con los espacios de grupo?
Sí.
Vale. ¿Es que estabas hablando? Vale.
No, perdona. ¿Te suena? No. Dímelo. ¿Sabes de espacios de Hilbert? ¿Sabes lo que es un producto escalar? Pues el espacio de Hilbert en dimensión infinita es como un espacio euclídeo, como Rn o Pn, pero en dimensión infinita. ¿Vale? Aquí son los vectores, aquí son puntos con n componentes. Lo que es importante es el producto escalar, ¿no? O sea, si quieres, ahora Daniel se va a cabrear porque voy a poner el conjugador. Ahí se ve que soy más. Vale. Es la manera de recompensarlo, por cierto, muy pronto. Un matemático siempre lo pone aquí.
Sí.
El por qué os lo digo si queréis en la Ok. Y entonces, si tienes un espacio de dimensión infinita, que es lo que vamos a tener, L2 son sucesiones infinitas de cuadrado sumable, y esto, en lugar de acabar en n, se va a infinito. Tienes una condición analítica. Y bueno, si quieres hablamos un poco después. Ahora sí empieza así.
Claro.
Y finalmente, ahí arriba existe una chi super X, entonces, ¿no? ¿Esta chi es una chi global o no puedo entender?
Una familia de... Sí, tiene razón. Sí. O sea, igual que antes tenías una familia de subconjuntos, ahora tienes una familia de aplicaciones que te meten en... Sí. Aquí quieres que ponga L2 de X. No. Exacto. No puede ser R, no. Deja ver que lo piense.
La aplicación sí va a decir si ya cada vez que esa función aquí tuve una aplicación de X a M, también de 2 se puede sumar.
No.
La X te la manda a los coeficientes de una función que vive en el...
Es que esto quizá ha confundido un poco. No, tiene que ser H. Tiene que ser H por esta condición de aquí. No, es que eso es lo que no... Eso lo he hecho porque he hablado demasiado. No estaba aquí en mi guión. Pero estaba adelantando lo que voy a necesitar mañana. Que ahí sí va a ser H. No, eso es quizá una confusión. Olvidar esto. Bueno, no lo olvidéis, olvidadlo hasta mañana. Y esto, bueno, vamos a ver qué hacer. Ok, no, by definition.
A lo mejor queda claro si dices cómo toma un elemento de X y cómo te devuelve un elemento de H. ¿Cuál es el elemento de X y cuál es el elemento de H?
Bueno, yo creo que una función característica la puedes ver como un elemento de H, ¿no? Que tiene, son unos en los puntos que están en H y ceros se te dan, si quieres. Esto lo puedes ver como una sucesión de unos y las etiquetas X están en y están en la sub X, pero es aquí. Y esto es un vector en X. ¿Perdón? Claro, esto me ha pasado para dar la idea de la demostración. Si habéis editado, pues nos quedamos aquí. O sea que sería L2 de H aquí, en la idea de la demostración, ¿no? Pero no lo quiero decir. ¿Ok? Quiero decir, eso ya es se puede realizar H como L2 de X si quieres, pero es más limpio para lo que voy a decir después, quedaros como 1, 2 y 3 romanos. ¿Ok? Pero sí, no es R, eso no puede ser R, seguro. ¿Eh? Bueno, okay, let's move on. No, it's recording. Okay. Okay, this is really a proof I would like to do for you, at least one of the directions, because we turn back to the quasi-isometries. Yeah? Let me state it, and then I will close the chapter 2, and maybe I have time to say a few things about operators. So I start chapter 3. So my motivation for mentioning Hickson Rowe's characterization is to, and what I'm saying now is just to tell you that this has more to do with Hilbert spaces, this property A, than one should think from its first definition. Okay, so let me write, this is the theorem of this lecture. XD on the geometry and A. Then let me write it correctly. Then there exists a coarse embedding into a Hilbert space. Then there exists a coarse embedding into a Hilbert space. I told you in the beginning that I had to do restrictions, and we restricted essentially to quasi-isometries. But I told you there are more general mappings which are the correct ones. This is not about the geometry metric space with A is not quasi. It's not a quasi embedding into a Hilbert space, but almost. One of the inequalities is like for quasi-isometries. Remember again, the quasi-isometry was a bound of the distance in the images with the dxx prime from above and from below plus constants C and B. Yeah? Okay. And the connection to quasi-isometries, this is something I would like to do for you. And the estimate, so if you remember, we have this. Oops. Okay, so this was a quasi-isometry. We will have this here, but for the lower bound, we have no bound with the metric. So there I will have a square root of n, which is one of those functions, row platform minus I introduced in the beginning. Yeah. So at this side, this is what I'm going to show you, that this is for the upper estimate is like a quasi-isometry. Yeah, and this is something that you can understand. To prove the theorem, really, I need to go to more general coarse equivalence notions. But I mean, it's not necessary this week. And I think it's enough if you halfway understand what is the idea. And of course, to prove this theorem, I need Higgs-Throws characterization. I need to have a Hilbert space at hand. Okay, so and this is what I'm going to use Higgs-Throws. The idea of the proof of one, a piece of an idea. Yeah, well, let's write proof in inverted commas 2 times, and I hope that's enough. So xt is A, and then in this characterization, every epsilon and every r positive. And you have my notes, so you don't even have to copy. And you believe more what I wrote than what I say. And then for any R, yeah, I want to make again a scaling of the radii with natural numbers because everything is discrete, it's very convenient. And epsilon is 1/2n. So I have the natural numbers anyway. And then since we have property A in this Hilbert space version, there exists an Sn for each n, for each natural number, for each value of the radius. There exists a positive Sn. And there exists a kind of map from X to a Hilbert space Hn, because for each radius and for each epsilon, I have a Hilbert space. So let me label the Hilbert spaces also with n. Okay. Such that if the distance between x and y is below Rn, this is the crucial in amenability and in property A. The really important condition is the isoparametric relation. Yes, so let me focus on this. So if we are closed, if the points are closed, then we know that the distance of two vectors, these two vectors, is below the position I have given to you. Yeah, in this case, as a function of it. This is the norm associated to the Hilbert space. Well, maybe you can speak afterwards. I don't want to. Yeah, there is a Hilbert space, is in particular a norm space, and I can just see what is the distance of the vector. Yeah, there is a lot of geometry behind the Hilbert space. Okay, so what is the picture here? So you have an X, and you have a sphere of radius 1. Then you have a sphere of radius 2. And so if my Y lies here, here is Y, say, yeah, if here is my Y, then the vectors in the Hilbert space, psi of X and psi of Y are at distance 1/2.
Pero esos son operadores, ¿no? No son vectores.
Son vectores, Max.
Funciones que van de X a H.
Sí, pero, o sea, para cada X, tú me das un X y yo te devuelvo un vector en el Hilbert. Eso es así.
X es el punto en el que evalúas el vector sí. O sea, el operador sí. Y lo que pasa es que antes ha habido una confusión porque ha cambiado un xi por una sucesión de xis, pero esos eran los elementos de H, no eran los elementos de X va a H. Y entonces la pregunta que ha hecho algún compañero por detrás estaba correcta. Los psi X son elementos del espacio de Hilbert. El psi
Sí, esto es un vector.
es el operador que embebe esos elementos. ¿Vale? Y luego, a lo mejor también os confunde que lo ha evaluado en un punto Z.
Sí,
del que
eso
luego se hablará.
ha sido un error, me doy cuenta.
Del que luego se hablará. Entonces,
Esto es un vector en H, seguro. ¿Vale? Y a ver si hasta mañana consigo algo. What I want to say is that this is in X. So you can think, if you like geometry, you can think of a fiber space. You have your X, and on each X you attach a vector. Yeah, kind of. Yeah. And so what this is here is saying is, if this is y1, the distance between psi of X and psi of y1 is below 2. But if your y2 is further away, so this is 2, then the distance between X, which is the center at which we are looking, and the psi of y2 is kind of closer. And so, yeah, so that's the description. Okay, but I promise you at least a kind of quasi-isometry from X into a Hilbert space. So how is this function defined? Yeah, construction. Of the map that almost looks like a quasi-isometry, and we are going to have one of the estimates like in quasi-isometries and the other one not. Yeah, but I will not do the other one, but this the first one is. Okay, so choose kind of X naught. Arbitrary root, you want a point, a distinguished point in X. Let me write this way. Okay. And now make the direct sum of all these Hilbert spaces. For each n, I have a Hilbert space. For one, I have one Hilbert space, H1, then H2, H3, and I do the direct sum as Hilbert spaces from 1 to infinity. Yeah? So H1, orthogonal sum H2, H3, and so on. And this is going to be the Hilbert space where I'm going to embed my metric space. And so how can I do it? Level X. So I need a map, a quasi-isometry. It's a map from X into H. Yeah? Quasi-isometries are mappings between metric spaces. And a Hilbert space is a particular metric space. Yeah, with the norm given by the scalar group. Okay, and this is going to be my Hilbert. And so, how do I define it? F of X is a sequence of vectors here. Yeah, how do I construct it? Well, it's the sum of the, or it's the overall sum I from infinity. I deleted Hickson floor characterization. This was here a mistake. No, it's not, because I have it there. So what I forgot is to write this. For any natural number and for any tolerance radius, I have a map from X into a Hilbert space. So I have a psi1 to H1, psi2 to H2. Yeah, and when I change my label 1, 2, 3, etc., I'm putting my closeness radius bigger, making my closeness radius bigger and bigger, and the difference here is smaller and smaller. Okay, so this is the difference. A note, of course, note that if x is equal to x0, then f of x0 is 0, because I'm subtracting one vector from the same one. Yeah? You will see why we need this kind of affine structure. Okay.
Can I ask a question?
Yes, sure.
That sum is with uppercase sigma, or with the, you put like the circle with the plus.
Yeah, because I'm summing Hilbert space vectors. What I want to say is that if I change n, yeah, so this Hilbert space here is, if you want,
Disjoint representation.
sorry?
You want to choose disjoint representations.
Yeah, I'm not summing in the same Hilbert space, but a point here is a collection of 1, 2, 3. This guy lives in H1, H2, H3. And I want to place this. This is a vector in Hn, and this subtraction is a linear operation in Hn at the component Hn. It's like summing components of vector. Okay. If I write here the normal sum, you may think that all these guys live in the same Hilbert space, but they change according to n. Okay. Okay. And the norm, maybe I should say the norm of V. So if V, wait, let's begin. V if V is an element in H1, H2, the norm of this vector squared, this is really the sum. The norms are, that's the norm of this vector plus the norm of this vector, and so on. It's a Euclidean norm. I promise you not to start with the raw. Yeah, I will stop. We can stop here within 5 minutes. So maybe you will have some time to recover. Okay. Maybe the change or the difficulty here lies in the fact that we are going to construct isometry or quasi-isometry or almost a quasi-isometry from X to H. So I was all the time speaking of quasi-isometries between X and Y. X metric space, Y metric space, and somehow in your head, now I changed the Y, but the Hilbert space is a metric space. The distance of two vectors V and W is just this here. So I may ask if there is a coarse embedding or a quasi-isometry like application from X, the metric space full of dots, to a Hilbert space. Why not? And in fact, the content of this theorem is telling you that a metric space with property A looks at large distance like a Hilbert space, which is a metric space. So in a way, it's a way of saying that something that is completely static, gets into a Hilbert space with linear structure, scalar product, orthogonality notions, etc., etc. That's really incredible. Okay. So this is a map from one metric space into a Hilbert space. Okay. I want to look at the difference of these two maps. Remember again my definition of quasi-isometry. I have to be able to bound above and below this number. Yeah, but in a Hilbert space, the metric is this one here. So I have to bound this number. If this is going to qualify as a quasi-isometry-like map, yeah, the distance in a Hilbert space is this one here. So the distance between two vectors is the square root of the scalar product of this difference. Yeah. So why not? This is my distance in a Hilbert space. So this I have to bound by the distance in the metric space. That's my aim. And I'm going to give you only, this is the end of my proof. Well, it's the end of what I want to say about the proof. It's an upper bound of this distance. Yeah, and you will see it looks like a quasi-isometry. Okay. So here is the definition of the map. And well, this is the sum of okay, because this is essentially the difference of each component. Yeah, my vectors are infinite collections. And I can take the difference component-wise, and then I look at the difference in each component. Okay, this would be more correct. No, I mean, you can embed it also in L1, and it's easier to estimate. But now, I was hoping that nobody noticed. Anyway, so I think I still can do. Conceptual. Now X and Y are fixed, and they have a certain distance. Some distance. Yeah, okay. And then I'm breaking the series into a finite sum up to an uppercase n, and then from n plus 1 up to infinity. Eso row funciona para LPs en general. Y de hecho la versión buena es N. Ok. Okay. Everybody understand. And now comes my point. I'm taking this, cutting uppercase n below that number. Right? So this guy here is below this distance. It's a number. And I'm sure I can get up to the boundary of that number. You can take the floor of distance. Okay, that's not an actual number. And then I sum up to that number. Yeah? And this one is bigger. Yeah? This is bigger than the distance of x and y. And why do I do this? Because the Hickson row condition and in general property A distinguish neatly between being close and being far away. Yeah. Okay, and that's smaller or equal than not the constant I have here, but still some constant c times the cardinality of minus. Okay. And this one here is what? Okay. Oh. You see the trick? When I'm close, I have a finite sum. And when I'm far away, I'm very small. Yeah? And this guy here is, well, in my estimate, it was 1/2 to the n, which sums up to, I think I can estimate this by, yeah, this is a converging sequence. Yeah, because well, I chose this epsilon. Maybe I can take a square root or something. Yeah. Maybe I have to put a square root here. But in any case, I'm summing up a series that is below 1. Yeah, you know that the sum. So this, what I'm exploiting is this. Yeah, this is a converging sum, and I'm starting far away. So I get a number which is below 1. Yeah? So altogether, I get following. The distance of this guy is below c times n plus 1 plus another constant. I don't really care here. But n was below the distance between x and y. So this is c times dx y plus 1. And that's a quasi-isometry. Maybe there is another constant. You do it. Okay, but you see that the image here is bounded away by a constant times the distance between x and y and another constant, which is the sum of the tail of this series, which is converging because I chose when I'm far away from the point, I'm choosing distances which go scale like 1/2 to the n, which is a converging series. Yeah? And to show this, I don't do, but you can read in Novak Yu's book. Then you can bound it below by square root of n. Yeah, so you need a coarse value. You don't get the 1/c dxy minus 1 as a lower bound, but still you need this more general notion of course equivalence. But at least the uppercase estimate, or the upper estimate of is like in quasi-isometry. It's very subtle and very difficult. You need to understand fully, but I hope you realize what the idea is. And why do I have to subtract these vectors too? Well, in particular, to get that the norm, that the norm of f of x is smaller than equal. Yeah? I need to renormalize and subtract a constant vector, because if I only leave this here, I'm summing vectors of norm 1, and then the sum could be infinite. Yeah? But this norm here, is important to show that the norm is fine. Yeah. Okay. Otherwise, so you need to have a reference vector to subtract. Otherwise, I'm not sure that quasi-isometry is not mapping to something which is infinitely normal. Yeah, this you cannot do. So you have to hit a vector with finite norm in a hit. Okay, this was super difficult. Take it as something that may happen, and maybe some pieces of the argument you get. You have to read it several times, but still, I hope I would like to stop here. Yeah.
El último paso, tipo de la raíz de, porque eso estaba al cuadrado y claro, a hacerlo la tarea a raíz, ¿no?
Sí, lo que quieras. ¿Dónde? ¿Aquí? Sí, pero está bien hecho todavía. Es que yo he cogido el 1. ¿Dónde quieres la raíz?
La cuestión es que te sobra espacio en realidad. O sea, que vas sobrado.
No metes la raíz, sigue siendo bien.
Sí, además lo que pasa es que yo lo había preparado para que le saliera 1. Porque no, que queda más bonito, ¿no? Pero es una cosa dramática, en realidad da igual. Es decir, queda mejor si pones ahí 1, ¿no? Pero bueno. Porque había cogido una serie que sumaba 1, ya con las estimaciones, pero bueno, no importa, lo que importa es que aquí puedes poner una constante b en la que te dé la gana, ¿no? Y conecta con lo que habíamos visto de cuasi-isometrías. Y hacia abajo no hay cuasi-isometría posible y necesitas la noción Coarse. Pero aún así, los espacios métricos con propiedad A son cachitos de espacios de Hilbert. Eso bueno, todavía no me lo creo. Venga, pues nos vemos mañana. Mañana son operadores y vamos a ver hasta dónde llego. Desde luego la demostración que quería. Bueno.